Okay, so in the last couple of lectures, we have been discussing about the ensemble learning method in general. So where we have a like a set of classifiers, and like those classifiers are the classifications by them are somehow combined either through voting or some other way to come to the final predictions. And we also discussed that those classifiers will have some kind of weight, uh, probably based on their performance on some held out or validation set. And also in so we considered two variants of this. One is the like random forest or the bagging, and another variant was the boosting. So in case of boosting, what we do is like the different data points or examples, like we assign weights to those data points. And so typically what we do is whenever we make a mistake, whenever the initial classifier makes a mistake on a particular data point, its weightage is increased, while the weights of the other data points which are correctly classified, they are decreased. And as a result of which the next classifier that is motivated or that has a greater motivation for correctly classifying the ones which were misclassified. But this may again come at a cost that the ones which were classified correctly by the first classifier, they may get misclassified. So the classifiers which we get this way, individually none of them may be much better than the other. But if we combine them and if we do the voting, then it usually turns out to be much stronger. So that is the idea of ADA boost. Now today we will discuss something else known, another boosting technique called gradient boosting. So gradient descent you have already studied. You have also already seen like how gradient descent and its very different variants are used to optimize a certain function. So this gradient boosting, it's a combination of gradient descent and boosting. So first let us see take a let us get a gentle start to it. So let us consider, so gradient boosting is a problem which can be used like it can be used for both classification and regression. The regression is easier, the classification is harder. So, so unlike ADA boost, where like the algorithm which we showed was mostly for classification, though it can be you extended to regression also. But similarly, this gradient boosting, this is mainly for regression, though it can be also be extended to classification. So let us consider that we have a set of observations. Each observation so it's a supervised learning problem. So there is a feature vector x and there is a corresponding label y. So the label yi is in case of regression it's a real number, in case of classification it's a discrete quantity. Now suppose there is a model f, any model f. So what that model will do is it will take xi, the feature vector, and predict some label yi prime. Okay. So in general, yi prime will not be the same as yi. So these two have to be compared using the loss function. Now suppose let us define what is called as the residual. The residual is basically the difference between the predicted y and the actual the actual y minus the predicted y. So, or which you can call as y prime. The simple difference. This I am calling it as the residual. So now what like if we are considering an ensemble method, so suppose we what is done is that we make a sequence of these kinds of models f1, f2, etc, etc. That's the same thing which we had done in case of this ADA boost also, where we had a sequence of different classifiers. Now each classifier can make predictions on any data point. So in the process, each of them will produce some residual. So let us denote by like for the mth model, let us denote the corresponding residual by Rm. So like Rm is basically the difference between the true level minus the level predicted by the mth like model. So now suppose somehow I have reached till Fm. This Fm model has been given to me. Like you may, like if you want, you can consider m equal to 1 initially. So that means what? That means we initially have got some model F, maybe some very simple model. Maybe it just predicts the mean of the of all the y's in the training set. So this is basically the residual or the difference between the true level and the predicted level. So the question is now how to get the next model F2. So the like in case of AdaBoost, we saw how that F2 is selected by giving importance to additional importance to those points which have been correctly classified. I mean, which have been misclassified and so on. In this case, what we are going to do is the next stage model is going to minimize the like this current residual. So whatever is the so basically what it will do is it will I will try to predict the residual itself. That is this difference. So F2 will not try to predict y. F2 will actually just try to predict this the value of this residual itself. So it is something, so we will call that, let us call that function hm, which can actually predict the residual Rm. So, now, so let us try to write it in formal language. So the initial the initial function, if we call that whether we call it f0 or f not, whatever, the idea is that I want to make a prediction which makes which is as close to the correct level as possible with respect to the loss function. So this is a general regression task. So like you can choose any model for this. Now now for Fm, like if you are, when you are considering the mth model in general in the mth sequence, so by then you already have got the m minus 1th model. So this model, it makes some prediction on x, on the feature vector x. So the question here is so what so this f this m minus 1, it will have it will not be predicting the labels perfectly, some residual will be left. So the idea here is that we have to, the mth model will have to be chosen basically in this way. Yes, so the fmth model is basically the f minus 1th model plus an additional thing called hm, which is basically a measure of the residual till this point. So that is, we can say that, so like if we write down, so the actual value is y. So the initial residual is, if we call it R0, that, okay, let me write it separately. So let's say that the initial residual is y, sorry, the true level is y, and the corresponding feature vector is x. So we have the initial residual is R0 equal to y minus f0 x. So where f0 is some simple model. Now what so what to so this is the residual which I have incurred. So ideally what should I try to do to get y? So that means so this obviously means y is equal to f naught x plus r naught. So if you want, you can write r naught x also. So if I can somehow from x, if I can somehow predict R naught, then I am done. Then I can just get just add that value to f naught and get y. So what I will do is learn some learn a function h such that h of x is equal to r naught x. So, for that, what will I do? I will, of course, like I have my training data. I have like the feature vector xi corresponding to xi. What I need to predict is the value of r naught xi. So what I do is I basically create a new data set. The feature vectors are unchanged, but instead of, so the initial data set looks like this, xi, yi. Now what I want to do is I now create a new data set which is like which is of this form, xi r naught xi. So that means at every x, for every xi, I calculate the value of r naught. That is, I make its prediction using f naught, which is the initial model, calculate the difference from yi, and accordingly define this way, where r naught xi is equal to yi minus f naught xi. Correct? So, so now what I do, so like I have to learn a mapping from xi to, so you can just forget that these are residuals. You can now imagine that I have got a different data set where these are the labels. So I find some kind of a mapping from xi to r naught xi. So I will let me call that as h. So hxi, that will so this like tries to predict r naught xi, but of course it will not be able to predict it perfectly. So what I get is r1 xi, which is equal to r naught xi r naught xi minus h of xi. You may call it as h1 also. Fine. So so now basically we can say that the estimate like that is, so initially f naught was my estimate of y. So now what you can say that my new estimate has become f naught x plus h1 of x. Okay, but still that is not equal to y. There is still a difference. What is that difference? That difference is r1x. Correct? So, so now what do I need to do? Now I have to just proceed in the same way. Now I create another data set. Like, so I now from xi, I now want to predict this r1 xi. So the new data set looks like this, r1 xi. Where r1 xi is defined as follows. This r1 just comes like this. So you basically, in every stage, you are using the same set of training points with the same feature vector, but their labels are changing. The initial labels were the actual labels. After that, like we replace them by the first order residuals. Next, we are replacing them by the second order residuals. Okay. And so what, like now what we will do? So obviously we will try to learn another function which we may call as H2. So what will H2 do? So H2 will try to predict this R1 Xi from Xi. Fine. So yeah, so what happened? So like yeah, so H2 Xi tries to predict R1 Xi. But of course, again, this time also the prediction will not be absolutely accurate. So what I will get is I will get the third level residuals like this. R2xi is equal to R1xi, sorry, it is, yes, it is R1xi minus H2xi, correct? And so, like, as you can understand that this process will keep on continuing. So my estimate of y initially was just f naught x. After that, my estimate of y became f naught x plus h1x. So if I want, I may call this as f1x. Okay. After this, my estimate improves to f naught x plus h1x plus h2x. And this I may call as my f2x. And then this process continues. It continues till either there is convergence, which means that I mean all the residuals for almost all the data points is 0. That means, so say suppose I have reached the mth step like this, where this happens. If this is reached, and this has to happen for all the training data points. That is, for all the training data points, the residual left is next to nothing. So if this happens, then I can say that I have converged. There is no need of any further thing. Alternatively, we can have some fixed like or maximum iteration. Let's say call it as capital M. So I can say capital Mx is equal to h1x plus h2x plus all the way up to h m minus 1 x.
Sir,
Fine. So this is this is where the your whole model converges. So either either you can say that you can stop this thing at after a fixed number of iterations, which you can call as capital M. That's a predefined number.
so can you hear me?
So
Hello.
it will be HMX.
Which one? This one, right? Huh. Sorry.
So can you hear me?
Yes. Yes.
So can we consider H1, H2, H3 as the terms of the a Taylor series?
Uh, in a sense, yes, and that is how actually the you are absolutely right. So it is so these are the terms. I mean, the Taylor series expansion is actually what we will use to actually try to estimate these things. So that is so far we have not used. So although we are calling it as a gradient boosting, so far in this treatment what we have done so far, we have not yet considered gradients. But when we consider the actually consider the gradients, you will see that it is the Taylor series coefficients which will become important. So yes, you are right. So like either we can do it for some predefined number of iterations, or we can just do it till convergence. That is at a time when we are not getting any further residuals. So this is basically the broad idea in a nutshell. But there are reasons. But there are of course reasons or practical reasons of that we do not do it exactly in this way. The reasons are that like finding a function h which that is minimizes the residuals and so on may often be a like a difficult task. So let us look at the different variants. So first of all, the simplest approach is just to try what we discussed now itself. And based on this, there is one algorithm known as the regression, the residual based regression trees, or sometimes it's also known as tree boost. So what happens in that case is that whatever the h functions which we are considering, that is at every step, these h's which we are talking about, these are all decision trees. That is h1, I mean not exactly decision trees, but they are all regression trees. Okay, I mean, I'm not saying that this is what we always have to do, but if we do this, like in case of the tree boost or the residual based regression tree algorithm, they are all the regression trees. So now the definition, so what happens in this case is that the definition of the loss function is relaxed. So what loss function? Now, so like here we are like in the formal definition, like basically we are choosing the h in such a way as to minimize some kind of a loss function. That is a loss function between the actual yi and like what has been the predicted yi till then. So they are compared using a some kind of a loss function. Now, if you see, in case of a decision tree, there is no, now in general, this is a hard problem. That is, if you have a loss function fixed, then choosing a classifier such that this particular loss function is minimized. I mean, this it may not always be the it may not always be an easy thing to do. In certain situations, it may be possible. It may be easy. In some others, in general situations, it may not be that easy. Now, suppose we are dealing with decision trees or regression trees. That is, at each of these h which we are talking about is a regression tree. So just a second. Huh? So now, if you remember the regression tree algorithm, in case of regression tree algorithm, when we are choosing the various parameters of the regression tree, we are not really minimizing any particular loss function. We are simply trying at every node, we are simply trying to minimize the entropy or the variance or something like that. So in a sense, we are taking the optimization which we are carrying out in case of a decision tree is localized. It's localized to each particular node. But it's so unlike something like say linear regression, where we basically define something called a loss function. So in case of linear regression, the like my predicted value is basically axi plus b, right? While my true value, the true observation is yi. So I define the least square loss function in the following way. Correct, I define my least square loss function like this, and then choose a and b as so as this thing can be minimized. So we are basically, we have an explicit loss function which we are like defining as say L, and then we are choosing the parameters of the model so as to minimize the loss function. In case of neural network also, it's the same thing. So when you studied neural networks, you would have considered various kinds of loss functions and the various parameters of the neural network, namely those edge weights which were calculated by backpropagation. They were all calculated with the purpose of what? With the purpose of minimizing the loss function. So there also you may have a squared error loss function, or if it is a classification, you have some other loss function. So by the way, when you are doing a classification using a neural network, what is the loss function that you use?
Entropy.
Yeah, it's not really entropy, it's rather the cross entropy. So basically what the neural network gives you is the probabilities of the different classes, right? So like if there are k classes, you get probabilities like p1, p2 up to pk. but your label is is only one of the classes. Let us say the label is class 2. So what you do is you define a probability distribution which is like a one hot encoding of the class label, that is 1 for the true label and 0 for everything else. So basically you get two probability distributions like this. Entropy is defined for one single probability distribution. That's what we deal with in case of decision tree. But here what we are doing is really we are comparing two distributions. One is the predicted distribution over class levels. The other is the actual distribution of the class levels. So like these two things can be compared using what is known as cross entropy. So like in case of these neural networks, the edge weights, which are basically the parameters, they are chosen as so as to minimize this cross entropy loss function. The closer your predicted distribution is to the true distribution, the lower will be the cross entropy. Similarly, in case of logistic regression, what is the loss function that we minimize?
Least square error.
No, least square error you minimize for in case of linear regression. In case of logistic regression, what do you minimize? So like you would have come across the term called logistic loss, like, right?
Is yi log yi plus
Yes,
1
yes,
minus.
right. That is the thing. So that logistic loss, if you think it is actually the cross entropy loss function for binary classes. That is for binary classification. That is there are two probabilities only, P1 and P2, and you have the the true levels are either 0, 1 or 1, 0. So the logistic loss function, what you just said right now, the y log y, I mean the log y, this kind of expression, right? Y log sigma of w transpose xi, right? Minus y1 log 1 minus sigma w transpose xi. This is the loss function which you minimize in case of logistic regression. This is sometimes called logistic loss, but it is actually the same as the cross entropy loss, which is used in case of neural network. So anyway, that's a different story. So what I am saying is that in case of decision tree, you may have noticed that there is no particular loss function which we try to minimize as such. The optimizations which we do is at the leaf level. So you can say that we are making local optimizations, but but there is no overall loss function which we are trying to optimize. So that is why some people consider the decision tree as largely a heuristic. That is, it does the ideally, according to the book definition of regression or classification, I mean a regression algorithm or classification algorithm, there has to be a loss function. I mean there has to be a function class, and there with us are with parameters, and there has to be a loss function. And basically, I have to like I will define this kind of thing, a loss function of the between the true labels and the labels predicted by your classifier with respect to its parameters, and then I will choose the parameters such that this loss function is is maximum. So the so the parameters are basically chosen in this way so as to maximize the minimize the loss function. Now, in case of decision tree, we do not have to do that. So we do not strictly follow this definition. So that's why that is we did not define a loss function like this. So some people say that decision tree is actually not a classification or regression algorithm. It is only a heuristic. It does not give any guarantees like this, that there is no particular function which it claims to minimize. So now, so theoretically, that might be a like a discredit for the regression for the decision tree, but in this case, it helps us to do something which we may not have found easy to do otherwise. So what it does is like basically at every stage we simply like as I was showing here, at every stage I construct a new kind of data set like this, and I build some kind of a mapping from the feature vector to the current estimate of the residuals, and that is done in this case by the regression trees. So we initially have a weak regression function on h naught x, which may simply be the mean. That is, you have all the y's in your data set, you just take the average value of them and just predict for any feature vector, you predict that value. So so that is an like initial weak regression function. So based on which you get your first round of residuals. Then you train a decision tree, or I mean, or if you want to put it, a regression tree that predicts this R naught x from x, and this regression tree you can call it as h1x. So similarly, so this will of course give you the next round of residuals which I showed you. So you will get a R1x. So accordingly you will build another regression tree h2, which takes the feature vector as input and tries to map them to the these second level residuals, and then this whole process continues for m steps or till convergence, so that the final prediction which we make is as follows. So this h naught x, this can be called as your f naught x, the initial classifier. Then I mean the initial regressor. Then h naught x plus h1x, this you can call your second level of regression. This you can call it as f1x. Then the third level, which includes fh2 also, that is called the got your next third level of regression, f2x, etc. So this way you finally get fmx, which you also call as your like fx. So this is the like the regression tree, like sorry, as you can call it as the residual based regression tree, or it is also given the nickname of tree boost. Tree boost means like a I mean a combination of regression tree and ADA boost. So it's like the boost part is something like a misnomer in this case. That is, we have not really done something like ADA boost. That is, we have not really increase the weightage to the functions. So I mean to the data points as such. But in a way, we have done that. See, like because like we are actually calculating the residuals. So those points where the prediction has been bad, so naturally they will have a higher value of the residual, and those points where you have like almost got it correct, they will have a lower value of the residuals. So that is when we are training this kind of a regression tree. This it's really that is, it does have the information of in which levels, so that some levels have high values and some levels have low values. By high I mean a high absolute value, and the others have low absolute value. So so when the decision I mean the regression tree is constructed, the magnitudes of the errors which you have made do play a role in that, though not in the way AdaBoost does. So that is, so like we can say that in some way we use the spirit of AdaBoost, but in a different way. Now if we let us come to the general formulation. So calculation of this residual, so if we just have any arbitrary loss function which is not specified and any arbitrary function class, then how to do this kind of a thing is generally a difficult problem. That is like what we do in case of normal regression is that we can choose the parameters of a function so as to minimize a loss function. That is the easy part. But here we are doing something much more complicated than that. Here we are trying to find a function from a function class for whom this kind of a relation holds, right? So this might be easy for some loss functions, but for a general loss function, like it is not easy. So when it is not easy, we like as one student was suggesting, we think of the Taylor series expansion. So what we do is like we write it in the following way. Just a second. What is hanging? Huh. So like we write, so we basically write the residual in this way in the form of a Taylor series expansion. So so the higher order terms we ignore, we just focus on the first term, which is like the gradient. So we so based on that, what we do is we write this kind of so we formulate the problem of defining the next level function fmx as some kind of a gradient descent problem or the steepest descent problem. So the gradient descent idea itself is based on the concept of the Taylor series expansion, right? So it's like you are what you are like in case of gradient descent, what you try to do is you try to so like you already have some current estimate of the optimal point, so you try to define it in the following way, right? Right, so that is you have the function which you are trying to minimize. You calculate this its gradient f at the point xm, and you like just multiply it with some kind of a gamma, which you can call as the learning rate, and so based on that you basically make the descent. That is you were initially here, you calculate the gradient, and basically you along the gradient you descend to another point by a quantity which is this gamma. This is the idea of your gradient descent. So in this case, the curious thing is that the things which we are trying, that is, we are now not moving over these xm's, that is the so these xm's, like these you can consider as real numbers or something. But what we are really doing is we are moving in the function space. That is, in a sense, we are calculate the gradient which we are calculating is the gradient of the loss function, because it's the loss function which we are. So here what the function which we are trying to minimize or optimize is this function f. So we are calculating its gradient with respect to what? With respect to x. So this gradient which we are talking about is basically this kind of a thing, right? uh, in this case, what the function which we are trying to optimize is this loss function L. And what we are trying to optimize it over is actually we are trying to optimize, we are trying to optimize it over this fm minus 1, which is actually a function itself. So it's not, so the derivative which we must carry out in this case, or the gradients which we must compute, are not with respect to x, but rather with respect to fm, or with respect to f, which is itself a function. So that may sound like a slightly arbitrary concept, but it is not. So it can be done. These kinds of gradients can actually be calculated in some situations. Say for example, if these consider this the squared error. The squared error is defined as like the true value is yi. The predicted value is at this stage is this thing. The value predicted by the m minus 1th stage regressor. So the loss function is simply the squared error, is the squared difference between the two. We just add a factor of half to it. So now if you calculate the derivative of this thing with respect to f minus 1 xi, okay, like if I take the derivative of this thing with respect to the quantity f minus 1 xi, so here don't get confused by the term xi. So xi in this case is something fixed. What you are trying to do, so although the feature vector xi is actually a feature vector, just consider that that is some fixed quantity. It's what the thing which is not fixed, or the variable thing, is actually the f of xi. right? That is what value we will predict at xi. So this xi you do not really even need to bother about. The thing that you should be bothering about is what value is being assigned to the corresponding to it by the function, that is the variable. So you take the derivative of this thing of this loss function with respect to the fm of -1 of xi, and you will just the what you will get is nothing but so the squared will come down as a factor of 2, but the half is there, so they will cross out. So I mean they will cancel out. So what you will be left with is just this thing, right? This is what you will be left with, but this is just the nothing but the residual, right? And now if you if you can for the purpose of gradient descent you can put a minus in front of it. So basically the gradient which you have calculated in this way is not, I mean this term is nothing but the residual itself. So so if this is the particular loss function which you must be which you should be using, then then your this update stage becomes fm x is equal to fm minus 1x. So what is the gradient? It is like minus gamma times the gradient which you have calculated, which is just hi, or or if you want to call it as the current residual, you can call it that also, r minus 1. Okay, since we are using h notation, let me write h only. Yeah, h m minus 1 x. Okay, so now we can see a very canny similarity between what we are writing now and what we were doing here. So what we were doing here is we that is fm, your fm x was equal to f m minus 1 x plus h m x, correct? So what we are getting here is yes, instead of calling it m minus 1, we can just call it as m. Yeah, so this, let me define it as hmx to make it just consistent with what we are writing earlier. Right, so so you can see that so earlier, so there I was writing fmx is equal to fm minus 1x plus hmx. Here I am writing minus gamma hmx. So that plus what was plus 1 has just been replaced by what is minus gamma. So you can we can see that what we were writing earlier, that is basically equivalent to this formulation in the special case that gamma is equal to -1. That's all. Correct. So so in general what we will do is, so this is of course done for a specific loss function, namely the squared error loss function. So but in for any other loss function, we will again have to calculate this gradient like this, and accordingly we will have to make a descent. Now what is this gamma? So gamma is the learning rate. So I can like in case of the gradient descent, which you may have studied, say neural network or things or any other case, say for logistic regression you may have studied gradient descent. So you may have discussed that this gamma, this learning rate gamma is set to some kind of a small value, 0.2 or something like that. And again, your choice of this parameter gamma, it can impact your convergence, right? So so you may have studied earlier that what are the disadvantages of this gamma being too low or being too high. Do you know that? What happens if gamma is too small or if gamma is too large?
If it is too low, it will take a lot of time to converge.
And too large?
And it may not converge.
Exactly. So that it is like we are we are initially here and we are slowly going down like this till this point. So if I am like if the gamma is too small, that means from here I am going here, then here, then here. That is, I am taking very small steps. So it may take a very long time to converge. On the other hand, if gamma is large, then from here I may jump to here and then jump back to here, then jump to here, then here. So I may never be able to reach this ideal point. So in general, the choice of gamma is a sensitive decision. So one thing which people do is what they call like is known as steepest descent, is that the gamma itself is chosen by some kind of a like a optimization problem. That is, that is like you basically choose that value of gamma for which this kind of a loss function is minimized. So like basically this is the full thing, that is basically if we try to minimize the loss function between these two things, right? But the if in but you fm is defined in the following way, which includes gamma. So the gamma is actually, you can treat it as some kind of a parameter of this function fm. So what we are doing effectively is that now we are like choosing that value of the gamma parameter for which this loss function is minimized. So that is actually what we do in general in case of any regression algorithm or any supervised learning algorithm, be it neural network or logistic, etc. We try to choose the parameters in such a way as to minimize the loss function. But the difference is that in case of neural network, the parameters which I try to minimize are the weights, the different weights of the edge weights. In case of logistic regression, what I minimize is basically the W transpose X. So this W vector. In case of, similarly, in case of linear regression, also the same thing. Here, the only parameter with which I am trying to minimize the loss function is not anything related to FM, but related to this step gamma. So so this is known as so basically you are choosing the step size gamma using and by solving an optimization problem, which you can call as the steepest descent. So now we have seen that this idea of actually is equivalent to the to what we are talking about earlier in the special case where gamma is equal to -1 and the loss function that is being used is the least square, I mean the squared error loss function. But like it is possible to use other kinds of loss functions also. We will look at some other loss functions, but before that, let us quickly summarize the algorithm, the general algorithm. So here, instead of residual, you define what is known as the pseudo residual. The pseudo residual is basically the gradient of the loss function at this point. So basically what I was telling you earlier, the loss function is what you need to minimize with respect to. So note that here the pseudo residual is defined for a particular data point xi. So this is, it is not a it's only for like you cannot define these kinds of pseudo residuals for any general data point. You have to define it for one particular data point and for the particular stage of the function. So I define the pseudo residual as RIM. It is different for the different data points as well as different for the different stages of the function. So the basically the crux of the algorithm is to design a function this HM which can predict the RM, that is the the pseudo likelihood for any arbitrary point or any fixed point X, which may be your test point also. Okay, so what we do is the algorithm is as follows. We have the initial training set as well as a differentiable loss function. This differentiable is important because we are having to calculate these derivatives. So if we are dealing with the classification problem, in classification, the simplest loss function we use is the 0, 1 loss function. That is I have a true label which is cat, and I have a predicted label which may be cat or dog. Yeah, like I just compare the two things. Where if they are identical, then the loss is 0. If they are different, then the loss is 1. As simple as that. That is the 0, 1 loss function. But as you can understand, this is certainly not a differentiable loss. In this case, I need a differentiable loss function. So that is why this kind of gradient boosting I cannot easily do for classification, because in classification what I am comparing is labels. So if I have to do this classification, I have to do a slight modification to the problem, which we'll just tell a bit later. So the generally what we do is we initialize a model with with maybe something like a constant value, which is f naught x, which may simply be the mean value. It may either be the mean value of all the y's, like something like this, or it can be like some common value of yi which minimizes the loss function, whichever loss function is being used. So if I am using this y bar as the as my initial estimate, then also I am minimizing a loss function only. I am minimizing the squared error loss function. So you can just convince yourself that if the loss function is the squared error, then the value which of f naught x which I should be choosing is the y bar, the common mean. But anyways, that's a different matter. So now what we do is we proceed in different stages from m equal to 1 to capital M, which is like the fixed number. So by the way, so just to repeat, I can either proceed for a fixed number of steps, a predefined number of steps, or I can just stop if I notice convergence at an earlier stage. So both things I can do. Now at any stage M, what do? I calculate these pseudo residuals. So what are these? And I calculate them for every data point separately, for every training data point separately. So what is the pseudo residual? As I said, the pseudo residual is simply the gradient of the loss function with respect to the current function which is being used. Okay. So once these pseudo residue, so basically you have to do this differentiation. So so that is why you need the loss function to be differentiable. If it is not differentiable like 0, 1 loss function, then you cannot do this. Once you do the differentiation, you get the RIM, which is the pseudo residual. And once again to remind, in case this L is the squared error loss, then the pseudo residual becomes equal to the actual residual. That is this thing. It becomes it becomes equal to the actual residual. Now what do? We feed some kind of a base learner. I mean, like some kind of a prediction algorithm, like which is like which it is like it is trained to predict this thing that is to predict the pseudo residual corresponding to every data point. So here in case of this algorithm, I was telling that you have to predict the residuals at every stage from the data point. But here I am saying that instead of the residual, we have to calculate the pseudo residuals. In case of the squared error loss function, residual is equal to pseudo residual. Okay, so so this HMX, so this is like basically that base learner which we are talking about, some kind of say regression tree or anything, any other thing also will do, whichever whatever you choose, which like takes xi, a feature vector, as input and predicts this corresponding pseudo likelihood RIM as the output. And then once you have chosen once you have selected that base learner, then you also have to choose this gamma. So how do you choose this gamma? That you do by by solving this kind of a optimization problem, what I said told earlier. That is, you have to define the loss function like this, and then minimize, so which of course is, I mean, it is defined in terms of the gamma, and then it is like optimized with respect to gamma. That is, I am choosing the value of gamma so that this is maximized, and then I update the model. So by the way, so here like they have written it like here it is written as plus. That's purely a like a matter of notation. So gradient descent is sometimes it is written, can be written in either of the two ways. It can be written either like this, or it can also be written as, different people write it in these ways. It all depends on what gamma you choose. So I mean the sign of gamma can be either positive or negative. So whether you write these as plus or minus makes no difference. Okay, so this way, so basically that's what you do. Like you choose the like for the steepest descent purpose, you choose the value of the optimal value of the learning rate gamma m, and accordingly you like you get the next stage model fmx, which is the previous fm minus x plus your current estimate of the pseudo residuals. And so like, and the whole process repeats like this, either for a fixed number of steps m or till convergence. So that is the like the gradient boosting in a nutshell. Now we have also now this thing can be done in various special cases. So like we can so we have already discussed that that is this tree boost thing we have already discussed. That is, if we, in the special case that all these base learners h which we are talking about, all of these are trees, and also the loss function is a squared loss function and the gamma is always m. In that case this just because like this algorithm becomes equivalent to the to the tree boost. Yes, otherwise also it is possible for you to use the this tree as those base learners or HM, in which case of course the structures of the tree, say the depth of the tree or the degrees, like they will vary from one stage to another. So which like it's like at every stage you have this kind of a data set, so you are fitting a tree to it. So now, of course, like how, like what will be the exact specifications of the tree? I mean, how, at what values you will split the different nodes, or how many ways you will split it, how many depths you will go. These are your choices, and they will vary from one stage to another. Now, like as I said, the loss function, like in the special case that the loss function, it's the squared error loss function, this becomes equal to the or identical with the tree boost algorithm. But it is possible to choose other loss functions also. So, so one loss function which people, or there are two other loss functions which people use. One is the absolute loss, another is the Huber loss. So one reason why people choose these kinds of loss functions is that they are more robust to outliers. So in case of the what I mean is that, so this is the squared error loss function. So suppose that there is an outlier function for which the true value of yi is very different, is going to be very different from what you are going to predict. So outliers, you know, right? Outliers are values which have, for which the label is very different from what it is supposed to be on the basis of the normal points. So if they like for example, if in a or like one dimensional case, so suppose if I plot xi like this and yi like this, so suppose like this is the, for most points the labels are like this, that is you can see a linear relation between xi and yi. Now there may be a point like this, so this point basically is an outlier. So whatever model you are fitting, say suppose you have fit this kind of a model, so obviously this model will incur a huge loss specifically for this point. And not only that, because because the difference is getting squared, that means what? That means this difference is actually getting amplified. I mean, whatever this difference was anyway very high, now we have made it squared it, so it will make it even higher. So that means the when I am choosing, or when I am trying to choose the parameters of this thing so as to optimize this loss function, it will actually try it will try to avoid the loss function being so high. So it will try its best to accommodate this outlier. It should not be, it will, the line which we will try to fit will not want to be very far away from the outlier. So it will end up doing being something like this. But in the process, it will end up antagonizing all these points. So that is so basically in the presence of outliers like this, the squared loss function, it does not do a great job. So I need other loss functions which are more robust to outliers. So the one way to do it is to use the absolute loss. That is, for every data point, I just calculate the absolute difference between the two things. I mean, between the true value and the predicted value. And then there is also something known as Huber loss, which is like midway between the absolute loss and the this squared loss. That is defined in the following way. That is, if the absolute difference between the true and predicted value is less than equal to some threshold, then I will go for the squared loss. On the other hand, if it is greater than that threshold, then I will do something like, which is something more like the absolute loss. Okay, so that is how they define the Huber loss. So this ensures that the outliers are that is for the points which are outliers, then this penalty is not so much as in this case, but for the non-outlier points, it is like it is this way only. So that is how you define the Huber loss. There are in general many other kinds of loss functions also. So, so in each of the cases, you can define, like you can like update the gradient by calculating. I mean, those gradients can be compared by basically taking the loss function of. I mean that by taking the derivative of the loss functions with respect to f, the current function, and so you can just verify that like these derivatives hold. And it's like a straightforward exercise. And once you have calculated these gradients, then you have to like update the residuals accordingly in the same way as discussed earlier. That is, you have to like you will get these like pseudo residuals, and then you have to train your model HXI as to be able to predict the pseudo residuals. So yeah, so the thing is, like in this yeah, so this h can, in this case also can be any kind of function, including the regression trees. So so in this case, the thing which we will be getting, it will not be the same as the tree boost. Okay, and finally the question is, so this we discussed is to be done only for regression. Right, because I am saying regression because this is suitable for regression, because it's only in case of regression that defining a residual like this makes sense. In case of classification, you cannot really define this kind of a residual. I mean, if your predicted label, if the true label is cat and your predicted label is dog, then you cannot really calculate a residual like cat minus dog, right? That is ridiculous. I mean, in case of classification problem, we are dealing with these categorical labels, which cannot, for which a residual does not make any sense. So now, if I
Sir,
yes,
for any specific case, is there any advantage of the absolute loss over the squared error loss?
that's what I am saying, right? The absolute loss is considered to be more robust to outliers.
Oh,
So if
sorry, I
you
was saying the other way around. The squared error loss
oh,
has any advantage over absolute loss?
okay, yeah. Yes, so the squared error loss has various statistical properties which are suitable for like which has advantages. I mean, the biggest advantage of the of this squared error loss is that like it is like easily differentiable at like all points. That is, when you have these absolute, then there is there is there is this point of singularity, right? In case of But while this one, like this is its plot is will be somewhat like this. So that's why the nature of the function is more amenable. So like if you have in general, when we want to do something like a gradient descent or something like that, people usually prefer the loss function, because it is easier to like calculate the gradients and descent along it and this kind of thing. There are also certain other convergence properties for which they prefer this kind of thing. But at the same time, as I said, it has its disadvantage with respect to outliers. Now, as I was saying that this loss like this classification, like when we are dealing with this. So suppose I want to solve a classification problem, then I cannot really define a residual like this. I mean, the residual itself is meaningless. So, so can you suggest some way in which this the classification problem can be adapted to this framework of residuals?
So if it is a binary classification problem, uh, then we can define the residuals in the same way.
How? I mean
Because
that, yeah, tell.
because we can say that define a threshold. If above that threshold, if the value is there, then we can assign a class to it.
No, no. I mean that is that there are two class levels, cat and dog. Let us say, and your y is equal to cat. The true value is cat. Now, at every stage, the classifier which you are learning is predicting some level, either cat or dog. So then, how will you? Then, where is the question of threshold coming?
I mean, we can define uh, ideal value of cat as 1, ideal value of dog as 0, and we can say if the predicted value is greater than 0.1, it is cat. Smaller than greater than 0.5 is cat. Smaller than 0.5 is dog.
Yeah, you are nearly right. Can anyone just improve upon that answer? You are almost there.
So we can use probabilities like upon averaging all the probabilities, averaging all the uh, labels, we can get the probabilities. Like if
Yeah, yeah.
0 1 0 0, then there will be 1 by 4, something like that.
Yeah. Like both of you are partially right. So basically, instead of predicting the label cat or dog, what we will be predicting is the probabilities of the different labels. So, like when I am say that is at every stage, what I will be doing is I will be predicting what is the probability that y is equal to, let us say, y1. What is y1? Y1 is, like, let us say, the first label in the label space. What is the probability that y is equal to y2 and so on? So, right. So if there are k possible labels, I just need to calculate these k probabilities. So if the now if so if I know that if the true label y is cat, that means I know that the first one, I mean the probability of that y is equal to cat is equal to 1, probability that y is equal to dog is 0. This is like this is what I know. So like it's like so what I am doing is that I am not saying that my output is I mean the output label is cat. I am saying that the output label is a this kind of a probability distribution 1 0, and at any stage the classifier, I mean the functions which I will be building, they will also give me a probability distribution over these class levels. So let's say 0.6, 0.4, or 0.321 and or 0.31, 0.69, something, some kind of a probability distribution it will give me at every stage. Okay, so basically the it is some kind, so I am reducing the this kind of a classification problem to a regression kind of problem, where the whichever models I am learning will give me not a single label but a probability distribution over all the like all the point, like all the class levels, right? Now that's what you do. That is precisely what you did in case of neural network also, in case of logistic regression also. In case of logistic regression, that is, so when you are using this term sigma of W transpose X for classification, what you wrote is that probability Y is equal to 1 given X is this thing. Similarly, probability that Y is equal to 0 or -1 with a given X is 1 minus this thing. That's how you define the this thing, your logistic regression. So in this case also, we will do the same thing. So the only problem here, so like basically whatever function we are defining, so it should be able to predict a probability distribution. But now in general, predicting a probability distribution is a difficult thing. I mean, there is no function there is no simple function which just takes in a feature vector X as input and predicts a directly predict some kind of a probability distribution as an output. So what it does is it will give you some vector and you will have to convert it into a into a probability distribution using a softmax function. So did you come across this softmax function in case of while dealing with the neural networks? Yes, did Jia sir tell about the
Yes.
softmax function? Yes, right. So it's like finally you at the the fully connected layer of the neural network, the final layer, it will just give you some values. So and then corresponding to your input, it will give you some arbitrary values. Then those arbitrary values you will pass through a softmax layer where you will basically do this kind of an operation, and then it will become equal to a probability distribution. Okay. So so in this case also, obviously, as I was mentioning earlier, the loss function can be the cross entropy. Like basically, you will have to the true that like you have a true distribution over the labels, which is basically the one hot encoding of the class level, and you have a predicted distribution. So somehow you will have to find or define a loss function to compare your predicted distribution with the true distribution. So it can loss function can either be KL divergence or the cross entropy. Both will work. So these are things which compare two probability distributions. They take a low value when the probability distributions are almost similar, and they take a high value when they are different from each other. Okay. The only thing is that in this case, for every class, you will need something like this WK. That is because there are k classes, you will define the probability of that particular class as in this type of way, WKX. So if there are k classes, there will be WK things like this. So when you are calculating the pseudo likelihood, that is by taking the gradient of the loss function, you will have to take the gradient with respect to all of these things. That is all of W1, like all of these W1, W2 up to WK. So your model will have lots of parameters. That is one parameter for every class. And these are not simple parameters also. Note that we are basically doing taking a dot product between this and a feature vector. So if your feature vector is d-dimensional, then each of these parameters are also d-dimensional vectors. So that is when you are calculating the pseudo likelihood by taking the gradients, here you will have to basically you will have to consider these kinds of vectors as your uh, for calculating the gradients, which may not be an easy, which is theoretically possible, but it's not. I mean, it's mathematically a bit more involved. So total kn number of likelihoods, pseudo likelihoods will have to be considered. So like earlier, you were calculating, like in the regression case, you are calculating the like at each stage you are calculating the pseudo likelihood for each of the data points. That is, n data points are there, so you calculated n pseudo likelihoods like this. In this case, in addition, that is for every data point and for every class level, you will have to calculate the pseudo likelihood. So total kn number of pseudo likelihoods will have to be calculated. And then you will basically you will have that is that is you will basically get that is you are getting for WM that is for each at each stage you will have to update these parameters uh, individually, right, for every value of k. So that is for every stage, you have to update each of the class specific parameters in the following way. Using the for the to calculate the gammas again you will have to use the steepest descent and so on. So that is what happens. So so this is how you do the this gradient boosting in case of the classification algorithm. It follows the same idea as the regression, but it because of the presence of these class specific parameters, it becomes more computationally complicated, and so you have to calculate so many of these residuals. Okay, so that is why this is ADA boost was something which was suitable for classification, though it can also be extended to regression, but this one is suitable for regression, but it can also be extended to classification. So this is the story of this gradient boosting, and with this we will also end our module on this ensemble learning, under which we calculated bagging, we studied bagging, random forest, data boost, and now gradient boosting. So till this is the syllabus of your first test, which will happen next week, that is 22nd, next Tuesday during these class hours itself. The exact so we will start at 8. It will go on till about say 9:30 or so. The test will be held in Moodle. The specifications, I mean, what kind of questions to be asked, etc. Those will be it will be mostly short questions or multiple choice questions, or one or two long questions may also be there, where we will actually have to write down the steps. So we will send out a detailed mail on this matter and maybe a bit later in this week. Okay. So we will take at this stage, let's take a 5-minute break. After this, we will continue on a new topic, which will not be for the next Tuesday's test.
So tentatively, how many questions will be there to solve in 1.5 hour?
So there will be a combination of short questions or MCQs, which may be 5 or 6, and there may be a few short answer type questions, maybe 2, and there may be one long answer question. But that is yet to be finalized. So those details we will communicate to you later this week.
So it would be very helpful if you could give us some sample questions.
Yeah, we will do that. We'll, like in the lab class, we'll do that.
Thank you, sir.
We will continue again at 9:30. Okay. And now let us continue on a new topic. So this is related to linear and nonlinear classifiers. So first of all, let us define what is a linear classifier. So by the way, first let me ask you one thing. Have you studied about the, like, has Jia sir covered the perceptron? Yes, perceptron, has it been covered in class? Yes, no?
No, sir. I
Okay.
don't remember.
Okay, fine. I'm assuming it has not been covered. Okay, so let us define the linear classifiers. So basically a linear classifier is it's some kind of a linear structure which basically divides the space into two half spaces. Now, which space we are talking about? Now we are talking about the feature space. So we have talked about, like as we know, the features are like for any data like data set, the features live in some kind of a space which we can call as the feature space. So this space can like it can be the like a d-dimensional real space or anything. In general, we assume it to be the d-dimensional real space, but it need not be that. It can be some other complicated space also. Now, now what when we now with respect to any space, like we can define this kind of a we can define what is a linear structure with respect to, like, if we so just let us restrict ourselves to the d-dimensional real space, that is this thing. So I can, so for whatever value of d I am considering, I can define some kind of a linear structure. So if it is a 2D space, that is if d equal to 2, then this is the equation of a line, as you can understand. If it is a 3D space, then it is the equation of a plane. If it is still higher dimensional, it is called a hyperplane. Now, what does a line do? So if you consider the normal 2D space, so any line like this, what it does is it divides the space into two parts. There is one on this side of the line and the other is on the other side of the line. And you can so now the expression of the, so this is a line in the 2D space, so we can write it. So like as you know, the equation of the line is something like we usually write it as ax plus by plus c is equal to 0. This is a way the standard way of writing the equation of a line. And you may also remember from when you studied coordinate geometry that in one half space, or like this happens, that is if you consider any point x comma y here, it will be like this. And if you consider any point here, it will be like this. Correct? And especially if but if you consider any point on the line, it will be equal to 0. So now instead of writing it like this, the equation of the line like this, ax plus by plus c, I can also write it in this way. So like typically when we are dealing with the feature space, I do not that is, I do not consider the two coordinates to be x and y. Rather, I consider the different coordinates to be x1, x2 up to xd. Now in the spatial case, that d equal to 2, like there are only two coordinates, x1 and x2. Right? So instead of writing it like this, x plus by plus c, I can as well write it as w1 x1 plus w2 x2 plus b, let's say b equal to 0. And this, as you can understand, w1 x1 plus w2 x2, this is basically the dot product between these two vectors, the w1 w2 vector and the x1 x2 vector. And this I can also write as W transpose X, where W is equal to W1 W2 and X we have already written as x1 x2. So, so if you are using this kind of a notation, then then basically the equation of the line is equal to W transpose X plus B equal to 0. Okay. Now sometimes we may do another trick, that is like instead of having a separate term like B, so this term is of course called the intercept. So instead of having a separate intercept term like this, we may also just append this feature vector x with an extra feature whose constant with constant value 1, so as to make it as a d-dimensional feature vector. And this b, I can just absorb it into the w vector itself. So, like this is also a plus 1 dimensional vector. This is also a d plus 1 dimensional vector. In this, of course, in the special case that d is equal to 2. So your W transpose X now becomes equal to, I mean, it's like this, X1, X2, 1 dot, sorry, like this is equal to this W1, W2, B dot X1, X2, 1. So as you can understand, this is nothing but equal to this W1x1 plus W2x2 plus B itself. So instead of writing W transpose X plus B separately, I can just write it as W transpose X, but it has to be understood that X is like it now contains an extra dimension whose value is fixed at 1, and W also contain an extra dimension which is basically the intercept. Okay. So now, as mentioned earlier, these kinds of this kind of a linear structure, it divides the hyperspace into two parts: the positive hyperspace where this W transpose X will be greater than 0, and the negative half space where it will be less than equal, I mean less than 0. And for those points which are lying on that linear structure, it will be equal to 0. Now, so using this concept, I can define what is known as a hyperplane classifier. So so we are considering now a binary classification task in which one class level I will define as +1, and the other class level as -1. Okay, so I will write it in this way. The hyperplane classifier is that for those points which satisfy this condition, I mean this condition, for I mean to say the points on the positive half space, for them y hat is going to be 1. That is, I take the sign of this quantity. So whatever value this is, I take its sign. So its sign will be +1. And for those points in the negative hyperspace, in half space, if I take its sign, it will be -1. Right? So this hyperplane classifier, it like basically it predicts the class level to be +1 on one side of the or in one half space, and -1 in the other half space. So that is what the definition of a like a I mean like a linear classifier. So now, suppose we are given a data set like this where the labels are binary. That is, there are only two class labels. Or let us say in this case, one is red, the other is blue. Now this data set, the question is this data set linearly separable or not? Now, what do I mean by linearly separable? What I mean is that can I find some kind of a linear structure like this, be it a plane or a hyperplane or line, whatever, such that all points of one class are on one side and all points of the other class are on the other side. Right? So in this case, clearly the answer is yes. If you consider this hyperplane or this line, it basically divides all the red points on one side and all the blue points on the other side. So now, if I so let us say that the equation for this line is W transpose X equal to 0, and in this is its positive half space, and this is its negative half space. So now suppose I define a rule that like this, or suppose I do this thing that the red points or the label red is mapped to the value of +1, and the label blue is mapped to the label -1. So in that case, if I define a hyperplane, yeah, a hyperplane classifier or linear classifier like this, which is basically predicting in this way, then as you can understand, it will have 100% accuracy. So like all the red, for all the red points, it will predict +1, but red and +1 are the same. And for all these points, it will predict -1, but -1 basically means blue. So all the red points will be classified as red, all the blue points will be classified as blue. So if we have this kind of a data set, then we call it as a linearly separable data set. Means there exists some linear structure with which I can like divide it into the two. I mean the points belonging to the two classes, I can separate or put them on the two different sides. Now, not all data sets are like that, not all are linearly separable. So take an example of this case. So here you have, again, you have red points and you have blue points, but there is this red point sitting in the amidst other blue points. Okay, so like you can of course call this as an outlier. But as you may understand, there is no linear structure, or there is no line which like has all the red points on one side and all the blue points on the other side. This point it will never be able to handle. So like even if you like this is one line which you are drawing. If you even if you draw a line in some other way like this or like this or any other way, you will never be able to have all the red points on one side and all the blue points on the other side. Okay, so so actually you can like try to solve it as some kind of a geometric puzzle that in that or try to prove this formally, that in this situation, why is it that you can never or why is it never be possible to separate the red and the blue points using a line. And you can actually try to generalize it and as a general puzzle in geometry, that uh, like which structures or which kinds of distributions of points can never be separated by a linear structure. So anyway, that is beside the point. The idea here is that there are some there can be some data sets like this which are not linearly separable. But the thing to be noted here is that except for this one point like this, and maybe like it may be possible to have a blue point sitting here also. So with the exception of the small number of rare points or outliers, the remaining points like you can still separate into the two, like using this kind of a linear structure. So this kind of data set we can call it as almost linearly separable. Means apart from a few exceptions, the rest of the points can always be that is, you can always find a line such that the rest of the points are like sorted according to class. That is, those belonging to one class lie on one side of the line, those belonging to the other class lie on the other side of the line, with a few exceptions. So this kind of data set we will call as almost linearly separable. Now there is another kind of data set which we can call as non-linearly separable. That means that, let us consider here. So like the red points are arranged like this in the feature space, the blue points are arranged like this in the feature space. So as you can understand, there will be no linear structure, no kind of line which will have the red points on one side and the blue points on the other side. It's not possible. But you can have a like if you define this kind of a circle, then obviously all the red points are inside the circle, all the blue points are outside the circle. So but the circle is like a non-linear structure. So it is not possible to separate these two classes by any linear structure, but it is possible to separate them using a non-linear structure. So this kind of a data set we call as non-linearly separable. And then finally, there is this kind of multi-layer separable. So like there is now a single linear structure or non-linear structure may not be able to separate all the points. But okay, maybe a non-linear structure can. I mean, a single linear structure cannot separate out all the points. But if you consider a combination of linear structures, then it can separate out the points. So like if you have a line like this, it's not that all the pluses are on one side and all the greens are on one side. There are pluses on both sides. On the other hand, if you consider this line, then also there are pluses on both sides. If you consider this line, then there are greens on both sides and so on. But if you consider a pair of lines like this, then you can always define some kind of relation like this. So for the let's say this is C1 and this is C2. So for the points which which lie in the positive half space of C1 but in the negative half space of C2 are to be considered as like green circles, while the points which lie in the negative half space of C1 or the positive half space of C2 are to be classified as red crosses. So one line alone is not enough to separate this data set, but rather the two lines to get taken together can be used to separate them. So this is like I don't know if you have considered this while studying neural network. This basically lays the foundation of a multi-layer structure, which generalized further, I mean very further, it develops into a like a neural network in the form that we know it. But this kind of a structure, it is actually possible to write it in the form of a neural network. Now, of course, there are some data sets which are inseparable. That means that there is no linear or non-linear structure where all the like the different classes can be separated, separated on the two sides. Now, which like if the data set is like this, then whatever structure you consider, you will not be able to have all the reds in one side and all the blues in the other side. So if this is the situation, then we say that the data set is inseparable. Okay. Now, the kind of algorithm or the kind of classification algorithm I will use depends on the nature of the data. So if the data is linearly separable, then what I will try to do is I will just try to find some kind of a separating hyperplane. That is, I will try to find one hyperplane such that all the points are one class are one side and all the other points are on the other side. That's called a linearly separable. But if the data you can if the data set is almost linearly separable, then also we can go for the hyperplane based classifier. Now, if the data is non-linearly separable, then there are two things which I can do. One is, of course, to use a non-linear classifier. That is like, as I was saying, this kind of a situation. So I will have to build some kind of a circle or some kind of a non-linear structure. So, and on the basis of that, I will have to do the classification. But it may also be that I may convert the data into some kind of a linearly separable form and then use a linear classifier. So this may sound rather strange at this point, but we will see later that it can be done rather easily. And finally, if the data is multi-layer separable, then we can use a multi-layer version of whatever we are using so far. Like if we are using a linear classifier, then we can have a multi-layer linear classifier, which is like the primitive form of a neural network. And finally, if the data is inseparable like this, then we cannot go for any like any of these things. So basically then we have to do something like a local structure. We have to look for local rules. We cannot build a, so in in the other cases we are building a global rule, some rule that will hold for all the data points. That is, like in this case I am saying that if any point is inside the circle then it is red, if some point is outside the circle it is green. So I am like this is an universal rule for all the data points. But in this kind of a situation, I cannot make any universal rule. So I will have to do some kind of a localized thing. So here I will have, that is, I will have to look for density, local densities of the different classes. So like for example, I may find a region here, right? For these points, I see that their labels are mostly blue. So there is a high density of blue points here. Similarly, here I find a high density of red points. Here I again find a high density of red points. Here again a high density of red points. So basically at different local regions, I will have to take the decisions locally. So things like nearest neighbor or Bayesian classifier, naive Bayes classifier, those things will be useful to us in this kind of a of an inseparable data set. Now, coming back to the situation where the dataset is linearly separable, that means there does exist some hyperplane which can separate the data into different classes. All the points belonging to class 1 will lie on one side of the hyperplane. All points of the other class will lie on the other side of that hyperplane. But so to do the classification in this case, it is enough to find any separating hyperplane. Now, of course, like we do not know a priori what that hyperplane is or how many such hyperplanes are there. It need not be unique. So if if it is not there, I mean, basically we have to find some hyperplane, any hyperplane which can separate the two classes like this. So one way to, so the simplest way of doing it is the perceptron algorithm. So what the perceptron algorithm does is, if it is a linearly separable data set, it will give you, it is guaranteed to give you one linear structure or one hyperplane such that all points are on one side of one class are on one side, or and all points of the other class on the other side. If it is not a linearly separable data set, if it is something else, then it can behave in arbitrary ways. That is, we cannot really give any guarantee about what it will do. But like if it is linearly separable, then you are convinced that it will give you an acceptable answer. Okay. So now what does, so like again we assume that there are two class levels, +1 and -1. Now what the perceptron does is it predicts according to the sign. So when the, so like this b term we will not consider from now on. I will, because we just said that the b I have actually incorporated or absorbed into the w. So the w is basically the w vector, the d-dimensional w vector plus the intercept b, and the feature vector x is like the d-dimensional feature vector plus the extra thing 1, extra feature 1. So this will the mathematically the two things remain same. I mean, whether you consider the bias separately or inside this is does not matter, but basically it will like make the writing simpler. That is, you will not have to consider the b separately. So now one thing which you have like for what we are, for what is going to come up after this, you remember this rule that uh, y into w transpose x greater than 0. If this condition holds, that means what? That means y and w transpose x, these two things have the same sign. Either both are positive or both are negative. I mean, that is the only way in which their product can be positive, right? If and we all know that plus into minus is equal to minus, plus into plus is equal to plus, minus into minus is also equal to plus. So if these two, this product is positive, that basically means that they have the same sign. But y can take the value of +1 and -1 only. And what this classifier is predicting is the y hat is just the sign of W transpose X. So that is also going to be either +1 or -1. But if it is so, if this thing is positive, then y hat is going to be +1. If this thing is negative, then y hat is going to be -1. Correct? Now, so fine. So now, like if we go to the perceptron, so what does the perceptron algorithm do? Is that its input is of course the label training data set with the feature vectors and their corresponding label. N of them are there, and the output is going to be the basically these things, which which we are decided to write as the W vector now. So the algorithm goes as follows. You initialize it as W0 and like the B is initially set to 0. Now this W0 can be any random vector. You can also start with the 0 vector if you want to. So now the algorithm proceeds as follows. For every training data point, so n data points are there, for each one you just see whether it is correctly classified or not. So like I said earlier, this product being negative basically means is a misclassification. That is the true level and the predicted level are having different signs. So there is misclassification. So if whenever there is a misclassification, you basically update your W according to the following rule. So W is like a vector you already have. W is a d-dimensional, I mean d+1 dimensional vector. So you just add the corresponding feature values multiplied by their label. So yi remember will be either +1 or -1. So like at any given stage, if W is, let us say 2.1, 3.2, 4.0, and the intercept, the extra intercept term, that is, let us say -3.5 at any stage. And let us say you have come across X, which is, let us say 0, 1, 0. Yeah, this is your feature vector. So then if you take the dot product, if you try to calculate W transpose X, what are you getting? 2.1 into 0 is 0, 3.2 into 1 is 3.2, 4.0 into 0 is 0, and minus 3.5 into the extra feature which is set to 1 is 3.5. So it is minus 0.3, which is negative. So now let us say that for this particular data point, the y, the label is +1. Okay, so the true label is +1, but what you have predicted is negative. So you can, as you can understand, y into W transpose X is going to be +1 into minus 0.3, which is minus 0.3, which is a negative, which means misclassification. Correct? So now that this has happened, what we have to do is we have to update the W in the following way. W is the new W is going to be the old W 2.1, 3.2, 4.0 minus 3.5 plus the sign, the yi is to be multiplied to each of these things, and the thing is to be added. So the y is of course +1, so like everything will remain as it is, 0, 1, 0, 1. Okay, and so the new W becomes equal to 3.1 sorry 2.1, 4.2, 4.0 minus 2.5. Okay, this is the updated value of W. So again, if you want, you can so this is the core part of W and this is the intercept term. So you can just do them together or do them separately. It's the same thing. So anyway, so you update W. So and then you do this cycle. You do this cycle over all the data points in the training set. Whenever you see any misclassification, you update W. Whenever you see any correct classification, you just ignore it. You leave W as unchanged. So this way you make a pass over all the n data points. Now you note how many mistakes you made in the whole pass. So if the so then after that you again start from the first point, because the first point you had tried to classify with respect to your initial estimate of W, which is W naught, but after that W has been modified many times. So again you have to start from the first point itself. Like you know what happens if you try to classify the first point with respect to W naught, but currently W is not equal to W naught, W is something else. So now we have to see whether the current W can classify the first point or not. So again, you will have to start from the first point and just repeat the process over all the data points. Whenever you see any error, you just update W, otherwise you just pass. And then again you repeat it over all the points and so on. You keep on repeating over all the points until any of the following stopping criteria are satisfied. Either is that all the examples are correctly classified in a single pass. That is, you have found a value of W with which all the points are correctly classified. If that is like if that happens, then you have been able to find the separating hyperplane. Or if a fixed number of iterations are completed. So just like in case of the this gradient boosting or ADA boost, we may have a predefined value that only these many trees are going to be allowed. So in this case also you may have a fixed number of iterations like this, after which you may stop. Or you may observe that W has converged. That is like at every mistake you are updating W, but W has become such that these changes do not, or these updates do not change W much. I mean, if suppose the values of W have become so high, say in the order of 10,000 or something, so that these adding these small numbers which are in the features does not make any difference. That also can happen. So if any of these uh, possible like these criteria are satisfied, then you can stop the perceptron algorithm. Okay. So that's the perceptron algorithm. So it's 10 o'clock. So we'll stop here, and we will see more on the about the perceptron algorithm in the next class. So next class is on Monday, but on Monday we'll have the class as usual. After that, on Tuesday during the class hours, we'll have the exam. So this perceptron, this is not part of your exam syllabus. Okay. So we'll stop here. Thank you. And we'll meet again in the lab.